Have you ever looked at something really complex, like a bridge or an airplane wing, and just wondered, how on earth do they know for sure that won't break? Well, these days, the answer is an incredibly powerful simulation tool. And today, we're going to pull back the curtain on that very tool, Finite Element Analysis.
So to really get why we even need something called Finite Element Analysis, or FEA for short, you've got to understand this fundamental problem that engineers are always up against. And that's the huge gap between the neat, simple problems you can solve with a pen and paper and the messy, complicated stuff you find in the real world.
Okay, look at this. On the left, you've got your classic textbook problem, a nice, simple, uniform beam. We've had exact equations for that kind of thing for ages. We know exactly how it'll bend and what the stress will be. But now look at the right. That's what the same kind of part actually looks like in a real machine. It's got holes, weird sections, stiffeners all over it. And those simple equations, they just completely fall apart. They're useless here.
Which leads us to the big question, right? For these super complex, real-world parts, how can we possibly figure out the stress and how much it's going to bend? How do we know if it's safe? Clearly, we need a whole new way of thinking.
And that new way of thinking is this absolutely brilliant method that basically revolutionized engineering. It's called finite element analysis.
The whole idea, the secret sauce, is this clever trick called discretization. So instead of trying to solve one single impossibly hard calculus problem for the whole part, we just chop it up. We break it down into thousands, sometimes millions of tiny, simple little pieces. And what this does is it turns an impossible math problem into just a really, really big algebra problem that a computer can actually solve. And here's what that looks like in action. The software creates what we call a mesh. Honestly, the best way to think about it is like building a really complex sculpture out of simple Lego bricks, right? Each little brick is simple, but when you put them all together, you can create almost any shape. The software is basically doing the same thing, just digitally, building up the object with this grid of manageable little finite elements. Now, if we zoom way in on this mesh, you'll see it's really made of just two things. You've got nodes. Those are the little points where the corners of all our simple shapes meet up. And then you have the elements, which are the actual shapes connecting all those nodes. And here's the key takeaway. The nodes are where all the calculations actually happen, and the elements just define the structure that connects them all together.
But before the computer can work its magic, an engineer has to very carefully build a digital version of the problem first. This whole setup phase has a name. It's called pre-processing.
And this process follows a pretty logical path. First, you get the 3D geometry ready, usually from a CAD file. Second, you create that mesh we just talked about. Third, and this is super important, you tell the computer what the thing is actually made of. And fourth, you define the physics of what's happening to it in the real world.
Defining the material is absolutely vital. This is where we tell all those little digital elements how to behave like real steel or aluminum or plastic. For a basic analysis, you really only need two key numbers: Young's modulus, which is just a fancy term for stiffness, how hard is it to bend, and Poisson's ratio, which describes that weird effect where if you squeeze something, it bulges out to the side.
Okay, this next step, this might be the most important one if you want to get a real answer. You have to apply the loads, which are all the forces and pressures the part is going to see. And then you apply boundary conditions, which are the constraints. This is where you tell the model, hey, this surface right here is bolted down, it can't move. You're basically telling the computer the story of how this part is actually used.
All right, so our digital twin is built, we've told it the whole story, and now we hit the solve button and hand it over to the computer. So what is it actually doing in there? What's the magic?
Well, it all comes down to this one single beautiful equation. Now, I know it looks a little intimidating with the brackets and all, but it's really just a supersized version of that simple spring equation you probably saw in high school physics. Force equals stiffness times displacement.
Let's just break that down real quick. We already know F, that's the forces we told the computer about. The computer figures out K, that's the overall stiffness of the whole thing, based on its shape and the material we picked. So the one thing we don't know, the entire reason we're doing this, is to solve for U, the displacement. In other words, how much does every single one of those nodes move?
So the computer crunches away and solves that massive equation. And what does it give us? A giant list of numbers. Yeah, kind of anticlimactic, right? This is where the last stage comes in, and honestly, it's the most satisfying part. Post-processing. This is where we turn all that raw data into these amazing visualizations. And just remember, the number one, most fundamental answer that comes out of that solver is displacement. That's the starting point. Everything else we want to know comes from that. And this is what it looks like. This is a displacement plot.
The colors show you how much things are moving, and engineers will usually exaggerate the shape change just to see it better. It's like an instant gut check. Is the part bending and twisting the way I expect it to? Does this make sense? So, once we know exactly how much every single node is moved, well, now we can figure out everything else. By seeing how much the little elements between the nodes got stretched, we can calculate something called strain. And from strain, using those material properties we defined earlier, we can finally calculate the internal forces, which we call stress. And this, right here, is so often the big payoff, a stress plot. The hot colors, your reds, your oranges, they show the spots with really high stress. This lets an engineer instantly see the potential weak spots, the exact places where a crack or a failure is most likely to start.
So to put that whole chain together, the computer solves for how much things move, that's displacement. From that movement, we figure out how much things stretch, that's strain. And from that stretch, we finally calculate the internal forces, and that's stress. See, it's a pretty clear logical path.
So when you put this all together, you realize that FEA isn't just a fancy calculator. It's really an insight tool. In a way, it's become the engineer's virtual crystal ball. This quote here really just hits the nail on the head. It's not just about solving these crazy complex problems. It's that the results, the stresses, the deflections, can be calculated in incredible detail. And most importantly, they can be visualized. You can actually see what's happening. And that matters to every single one of us. Because of FEA, engineers can test dozens of different ideas on a computer before they ever build a single physical thing. It lets them make sure a design is safe, lets them make parts lighter and cheaper, and ultimately it helps them innovate faster to create better, safer, and more efficient products for all of us.
It really makes you think, doesn't it? When you have a virtual crystal ball this powerful, one that lets you see the invisible forces inside almost anything you can imagine, what will engineers design next? The possibilities are just about endless.